time. You can't see it, you can't hear it, you can't wait, but we experience it every moment. The whole piece of time is a landscape, and we move to it slice by slice. But do we really understand time? Is time same for everyone? To understand time, let's go back in time and make a small journey to a certain young patent clerk, Albert Einstein. Imagine you are traveling just like other people in a train moving at a certain uniform speed. The train, relative to the outside environment, is in motion. You and the other people in the train, on the other hand, observe each other as a stationary object, as both you and the train are moving at the same speed. Hence, relative to the train, you are stationary, and the laws of physics stay same inside the train as they would in the ground when you're standing still. Let's consider you get off the train and observe it across moving in front of you. Now, you are stationary, and relative to you, the other people is moving with the same speed as the train. This is the phenomenon of relative motion, and we observe it every day. Does anything in the universe observe this relative motion the same way? Yes, everything except light. Light behaves in a different way. Imagine you have a light clock with you. This light clock has two mirrors in the opposite direction and the light beam bouncing in between them. Now, let's say the distance between the two mirrors is d, and the time for the light to travel that distance is t. For the sake of simplicity, let's say it's 1 second. So, when this clock is with you at rest position, the light bounces between the mirrors covering distance d in 1 second, which gives us the speed of light s. Now remember, speed is distance per unit time. Now, consider Albert Einstein also possesses the same light clock with you, only this time, he's traveling in a spaceship along with the clock. When Einstein travels in a certain speed, the clock travels with the same speed of the spaceship. Here, light has to travel an extra distance in the same 1 second. Let's consider its distance to be capital D and represent the speed of light here as capital S, which is to be greater than small s. But something's wrong here, because in the late 1800s, the Michelson-Morley experiment tried to detect the relative motion of the matter through an ether and concluded that the speed of light is constant. This cosmic speed limit is known as c. So in our little scenario, small s and capital S are equal. So the speed of light for both you and Einstein to remain constant, something has to give way. That something is time. It turns out, time slows down when you travel faster and faster during the speed of light. So, the faster Einstein traveled, the slower the time passes by. could be a day for Einstein in space could be as much as 50 years for you in the ground. This became the fundamental conclusion of the theory of relativity, a theory proposed by Albert Einstein in 1905. This theory broke the traditional understanding of time as a constant entity and proved that the time impact is different for different observers.